Okay, so today we're going to talk about histograms. We are on page 51, histograms. You guys have done histograms before. Okay, histograms is basically taking the frequency thing that we just did, right? We did the frequency tables, right? We did the cumulative. So we had three things, right? What did we learn? What were the three different things that we did? We did frequency table. What else did we do? Relative frequency table, right? Which is nothing more than the frequency table, and you divided it by the total to get the percentages wise, right? And then you did the cumulative frequency, right? Okay, so those are three things that we did. Okay? So we're going to take the frequency table data that we had, and all we're going to do is put them in a histogram. We're going to put in a bar chart. Well, not a bar chart, right? We will learn soon that a bar chart and histogram are two totally different things. Okay? All right. So histogram, let's go to page 51. Look at the bottom. At the bottom, you have the same exact looking graph there, right? What's the difference between the two?
Relative frequencies.
One has the frequency on the y-axis, the other one has the relative or percent relative frequency, right? So in other words, you took, on the left-hand side, you have the raw data, right? How many of each were there, then you converted that into percentage, and then you drew the relative frequency histogram. So we can see the difference between the relative frequency histogram and the histogram, right? The shape are always going to be the same, correct? Right? Because all you're doing is taking the frequency, taking the frequency table and dividing it by the total number. So the shape of the two should be the same. Okay? Let's go ahead and pick on Eliana to read the definition of a histogram there on top.
A histogram is a graph consisting of bars of equal width drawn adjacent to each other unless there are gaps in the data. The horizontal scale represents classes of quantitative data values and vertical scales represents frequencies. The heights of the bars correspond to frequency values.
Okay? All right, so everybody good on that? Now I'm going to two separate words that I'm going to point out from that definition. Okay, first of all, it said that the graph consists of bars of equal width. Okay, in other words, your bar widths have to be the same. Okay, if they're not the same, what can happen? So if I had a histogram that looked like this,
You kind of like visually squeeze the data, like you visually see it.
can you see that this guy looks really, really small?
Yeah.
Even though if you drew it correctly, it wouldn't be, correct? So this would be one of the classic ways to misrepresent the data, right? It's the same data. You have a graph, but you're actually misrepresenting it, right? Because it is not drawn with equal width, okay? So that's one of the things we'll talk about later on, okay? That's one thing. The other thing I want to point out is that the horizontal scale represents classes of quantitative data. Has to be quantitative data. Okay? We will have for categorical data, we will draw something that is very similar to this. Okay? And that is called a bar graph. Okay, that's different, right? A bar graph actually has spaces between each category. Okay, and that's how you differentiate between categorical data and quantitative data. Okay, today we're talking about quantitative data. So we will not be talking about a bar graph, we'll be talking about a histogram. Again, it looks similar, totally different data though, okay? Bar graphs are categorical, whereas histograms are quantitative, okay? Flip the page, let's go to page 52. Page 52, we have common distribution shapes. A, B, C, D. Okay, go with B first. B is what we call a uniform distribution. Right? They look the same all across the board, right? Doesn't matter what your class with, whatever you are, they all are pretty much the same. They're equal. Uniform distribution. Okay? Or, yeah, they're not down to them. That's, you know what, really is actually the same, but they're close enough, right? A, we call this one a roughly symmetrical, right? It is kind of, if you look at 100 to be, you know, the middle point there, it's roughly symmetrical on both sides. This is generally we talked about this, a normal distribution, correct? Right? Normal distribution bell curve looks like this, right? Okay. So it's roughly symmetrical. Now C and D are skewed. Okay, look at C. C looks like this. Okay. And all the data is pretty much on the left-hand side, right? Most of the data is on the left-hand side. So we call this skewed right. Okay, so it's kind of counterintuitive here, okay? It's skewed to the right. We call this data skewed to the right. Even though you would think, well, all the data's on the left-hand side. You would think you would call it skewed left, but we call this skewed right. Okay, a way to remember this, the book shows you, page 53, there's some random feet there. Okay, what that means is that look at that feet. Which foot does this look like? Does this look like the left foot or the right foot? The right foot. Therefore, it's skewed right. Okay? Another way to remember this is that think of a guy skiing down. You're skiing down to the right. Skewed to the right. Okay? All right. So yeah. Does not, as you know, you would think, but it's the other way around. Okay? All right. Skewed right, skewed left. Okay, make sure you understand that. Okay, so we got that. And in part 2, we said we have assessing normality with a normal quantile plot. If you flip the page, this is what we call a normal. There are normal quantile plots. You guys are, I'm never going to ask you guys to produce a normal quantile plot. All you have to do is be able to interpret one. If you look at the one on the first one, okay, you can see that the points are pretty randomly spaced there along the line, right? Some are a little higher, some a little lower, but they're pretty random. Okay? Whereas the middle one and the right one, you can see there's a definite shape to the points, right? The one in B, you can see that the B one, and the one in the middle one, that's not B, the middle one, this is the line, and you can see there is a shape that looks like this, correct? You see that? Okay. There's definite shape, and also along with the one on the right. There was a definite shape of how the points are there, okay? So that means that it is not a normal distribution. Remember we talked about the normal distribution? We said that all the statisticians want to make sure or try to get their distribution to be a normal distribution. This is one of the ways to fail that, okay? When you do this normal quantile plot. Okay, if you do the plot and there's a definite pattern, it is no good. It is not a normal distribution. So you're looking for true randomness of the points. Okay? So don't worry about trying to figure out how to produce one of these. All you need to be able to do is look at one and make a determination whether or not it is a normal distribution or not. Okay? We good there? Okay. We're good for the day.